Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Neptune, the eighth planet from the Sun, sits at the outermost edge of our solar system, a distant sentinel of icy darkness and swirling storms. Unlike the fiery inner worlds or the massive gas giants that dominate the middle of the solar system, Neptune embodies a striking contrast. A cold, distant world shaped by winds so fierce they dwarf the storms of any other planet. Often called the windy ice giant, Neptune has intrigued astronomers since its discovery in 1846, presenting a planet that seems both alien and majestic in its remote solitude. Its cobalt-blue hue hints at the secrets beneath its cloud tops, secrets that continue to inspire curiosity about the nature of planets at the edge of the Sun's influence. The discovery of Neptune is itself a story of human ingenuity and mathematical triumph. Unlike Mercury or Venus, which can be observed with the naked eye, Neptune eluded astronomers for centuries. It was only through careful observations of Uranus's orbit, which showed unexpected deviations, that scientists hypothesized the presence of another planet exerting gravitational influence. The mathematical predictions of Urbain Le Verrier in France and John Couch Adams in England led astronomers to the precise location where Neptune would appear in the night sky. Johann Galle at the Berlin Observatory confirmed the planet's existence on the very first night he searched, a testament to the power of reasoning and observation in the 19th century. This method of discovery, entirely dependent on calculations rather than chance observation, marked a turning point in astronomy, proving that unseen worlds could be revealed through the understanding of celestial mechanics alone. Neptune's atmosphere is a subject of fascination for astronomers and planetary scientists alike. Dominated by hydrogen, helium, and traces of methane, it is the methane that gives the planet its vivid blue coloration. The absorption of red light by methane molecules allows only the blue and green wavelengths to scatter, painting Neptune with the mesmerizing azure that has captivated generations of stargazers. Beyond its striking color, Neptune's atmosphere is turbulent and dynamic, featuring winds that are the fastest in the solar system. Speeds reach up to 2,100 kilometers per hour, far surpassing even the most ferocious hurricanes on Earth. The reasons behind such extraordinary wind velocities remain a puzzle. Some theories suggest that internal heat plays a role, with Neptune emitting more energy than it receives from the Sun, creating convection currents that drive the extreme weather. These internal processes, combined with the planet's rotation, give rise to enormous storms that can span thousands of kilometers, appearing and disappearing over the course of weeks. One of the most famous of these storms, first observed by the Voyager 2 spacecraft in 1989, was the Great Dark Spot. This colossal storm system resembled Jupiter's Great Red Spot, but was transient, vanishing only a few years after its discovery. It demonstrated the highly variable nature of Neptune's atmosphere, where storms can form rapidly and dissipate just as quickly. Surrounding these storms are bands of clouds that move at different speeds and directions, creating a chaotic and constantly changing pattern in the upper atmosphere. Observations from the Hubble Space Telescope and ground-based telescopes have continued to monitor these phenomena, revealing that Neptune's weather is more complex than previously imagined, with smaller dark spots and bright clouds forming and disappearing with remarkable frequency. Beneath its turbulent atmosphere, Neptune hides a world of ice and rock. Unlike Jupiter and Saturn, which are predominantly composed of hydrogen and helium, Neptune contains a significant amount of what scientists refer to as ices, including water, ammonia, and methane ices. These materials exist under extreme pressures and temperatures, forming a dense, slushy mantle surrounding a rocky core. The presence of these ices gives Neptune its classification as an ice giant, differentiating it from the gas giants that dominate the outer solar system. The internal structure of Neptune suggests complex interactions between its layers, possibly including the generation of magnetic fields through the movement of electrically conductive fluids. Indeed, Neptune's magnetic field is tilted and offset from its rotational axis, unlike Earth's, hinting at unique dynamo processes operating deep within the planet. Neptune also possesses a retinue of moons and rings, though they are less prominent than those of Saturn. Triton, the largest moon, is a world unto itself, with geysers of nitrogen gas suggesting active geology and possibly a subsurface ocean. Intriguingly, Triton orbits Neptune in a retrograde direction, indicating that it was likely captured from the Kuiper belt rather than forming alongside the planet. This capture event could have had profound effects on Neptune's system, possibly influencing the orbits of other moons and contributing to the planet's dynamic environment. In addition to Triton, Neptune has a collection of smaller moons, each with unique characteristics, from icy surfaces to cratered landscapes. Neptune's rings are faint and composed primarily of dark particles, yet they reveal the ongoing processes of dust generation and moon ring interactions that continue to shape the planet's surroundings. Voyager 2 remains the only spacecraft to have visited Neptune, flying past in August 1989. Its brief encounter revealed much about the planet's atmosphere, magnetic field, rings, and moons, transforming Neptune from a distant point of light into a dynamic and intriguing world. Images from Voyager 2 captured the swirling clouds, bright methane clouds, and massive storms, providing a glimpse into the relentless energy driving the planet's weather. Instruments aboard the spacecraft measured temperatures, wind speeds, and magnetic fields, laying the groundwork for future research. Since then, telescopes on Earth and in orbit have continued to study Neptune, confirming that its atmosphere remains active and that its magnetic and gravitational fields are unusually complex. Yet many mysteries remain, from the detailed composition of its interior to the mechanisms fueling its supersonic winds. Neptune's position in the solar system, far from the sun's warmth, makes it a world of extremes. Solar energy reaching Neptune is only a fraction of that received by Earth, creating frigid temperatures near -220 degrees Celsius. Despite this, the planet radiates more heat than it receives, suggesting that residual energy from its formation or ongoing internal processes contributes to its atmospheric dynamics. This combination of cold sunlight and internal heat drives the unique circulation patterns that produce Neptune's supersonic winds and massive storms. Unlike Earth, where solar heating is the primary driver of weather, Neptune's internal heat may dominate, making it a laboratory for understanding atmospheric processes under exotic conditions. Neptune's discovery also reshaped our understanding of planetary formation and migration. Its existence, predicted mathematically before it was observed, demonstrated the importance of gravity and orbital dynamics in shaping planetary systems. Moreover, Neptune's location and mass suggest that it may have migrated from a closer orbit in the early solar system, influenced by interactions with other giant planets. Such migrations have implications for the distribution of Kuiper belt objects and the overall architecture of the solar system. By studying Neptune, astronomers gain insights into not only the planet itself, but also the processes that sculpt planetary systems throughout the galaxy. The winds on Neptune, a defining characteristic of the planet, have fascinated scientists for decades. They are not only fast, but also exhibit complex patterns, including jet streams, vortices, and storm systems that shift with the seasons. The planet's axial tilt of about 28 degrees creates seasonal variations over its long orbit of 165 Earth years, influencing the distribution of sunlight and potentially the intensity of storms. This combination of rapid winds, extreme cold, and seasonal changes creates a dynamic and ever-changing environment, making Neptune a planet of perpetual motion and celestial drama. Observations continue to reveal that even the faintest features in Neptune's atmosphere can evolve over weeks or months, highlighting the planet's extraordinary atmospheric activity despite its distance from the sun. Neptune's moons, particularly Triton, offer another layer of intrigue. Triton's surface is dotted with frozen nitrogen, geysers, and smooth plains, suggesting geological activity despite the extreme cold. The retrograde orbit implies a volcanic capture, potentially causing tidal heating that could still influence the moon's interior. Other smaller moons, like Proteus and Nereid, present a variety of surfaces, from heavily cratered to relatively smooth, reflecting a history of collisions and gravitational interactions. Studying these moons provides a window into the processes that occur in the outer solar system, revealing how even distant planets can host complex and evolving systems. The faint rings of Neptune, though less spectacular than Saturn's, are dynamic and tell a story of ongoing evolution. Composed mainly of dust and small rocks, the rings are clumpy and uneven, hinting at gravitational influences from nearby moons. Observations suggest that the rings are relatively young and may be replenished by material from collisions or moon erosion. These rings, though subtle, add another dimension to Neptune's identity as a complex and active planet, demonstrating that even the most distant giants are not static but are shaped by interactions with their satellites and environments. Looking beyond the immediate features of Neptune, the planet serves as a gateway to understanding the broader cosmos. Ice giants like Neptune are common in exoplanetary systems, yet they are absent from the inner regions of our solar system, prompting questions about planetary formation and distribution. By studying Neptune, astronomers can test models of planet formation, migration, and atmospheric dynamics under conditions that are not easily replicated on Earth. Its extreme weather, icy composition, and unique magnetic field offer insights into the diversity of planetary types that populate the universe. In this sense, Neptune is not just a distant world in our own solar system, but also a touchstone for understanding planets far beyond, illuminating the processes that create worlds in the cold, dark reaches of space. Beneath Neptune's vivid clouds lies a hidden, complex interior that continues to intrigue scientists. Unlike Jupiter and Saturn, which are largely dominated by hydrogen and helium, Neptune's composition includes a dense mixture of water, ammonia, and methane ices surrounding a rocky core. This mantle of icy materials, existing under extreme pressures and temperatures, creates an environment unlike anything found on Earth. Scientists describe this region as a hot ice layer, where the distinction between solid and liquid becomes blurred under such conditions. The interactions within this mantle may drive internal heat and influence the convection patterns responsible for the planet's supersonic winds. Understanding the interior is crucial because it holds the key to Neptune's formation history, the generation of its magnetic field, and the energy that powers its extraordinary atmospheric phenomena. Neptune's magnetic field is another source of fascination. Unlike Earth's relatively aligned dipole field, Neptune's magnetic field is both tilted and offset from the planet's rotation axis. This unusual configuration suggests that the dynamo generating the magnetic field operates not from a central core, but from an outer shell within the ice mantle. Such a mechanism may be linked to the movement of electrically conductive fluids, possibly a combination of ionic water, ammonia, and methane under high pressure. The resulting magnetic field creates auroras near Neptune's poles, though these are far less studied than those on Jupiter or Saturn due to the planet's distance. These auroras hint at complex interactions between the solar wind and Neptune's magnetosphere, demonstrating that even at the solar system's edge, space weather plays a significant role in shaping planetary environments. Seasonal changes on Neptune occur over extraordinary timescales, owing to the planet's long orbital period of 165 Earth years and its axial tilt of 28 degrees. Each season lasts more than 4 decades, producing slow but significant variations in solar illumination across the planet's hemispheres. These changes influence cloud formations, storm activity, and the brightness of atmospheric features. Observations over the past few decades suggest that Neptune's climate is surprisingly dynamic despite the low levels of sunlight it receives. The interplay between internal heat and seasonal solar variations may explain why storms can form rapidly and dissipate unpredictably. This combination of factors creates a planet where change is constant, yet on a timeline so vast that human observations capture only brief snapshots of its ongoing evolution. Neptune's moons add another layer of complexity and wonder. Triton, by far the largest and most captivating, presents an icy, geologically active surface. Its retrograde orbit suggests it was captured from the Kuiper Belt, a dramatic event that likely altered the dynamics of Neptune's satellite system. Triton's surface features include nitrogen geysers that spew plumes into the thin atmosphere, smooth plains that hint at cryovolcanic activity, and scarred terrain shaped by both impacts and internal processes. Beneath its frozen exterior, Triton may harbor a subsurface ocean raising intriguing questions about its potential to support exotic forms of life. Other smaller moons, such as Proteus, Nereid, and Larissa, each contribute to Neptune's intricate gravitational web. Their orbits, surface compositions, and interactions with the planet and each other reveal a miniature solar system in its own right, shaped by collisions, tidal forces, and the capture of external objects. Neptune's faint rings, though subtle compared to Saturn's, are dynamic and revealing. Composed mainly of dark dust particles and small rocks, the rings appear clumpy, suggesting that they are relatively young and possibly unstable. Some regions of the rings are maintained by shepherd moons that confine the particles through gravitational interactions. The clumps and arcs within the rings hint at ongoing processes of erosion, collision, and replenishment. Studying these rings provides insights not only into Neptune's immediate environment, but also into the mechanisms that shape ring systems throughout the universe. Even in the frigid outskirts of the solar system, processes of formation, destruction, and evolution are actively at work. Voyager 2's flyby in 1989 provided humanity's first close encounter with Neptune and its system, transforming the planet from a distant point of light into a richly detailed world. The spacecraft revealed the fast winds, bright methane clouds, massive storms, and intricate moons, offering a glimpse into the complexity of the ice giant. Despite its brief encounter, Voyager 2 collected data that continued to guide research decades later. Observations confirm that Neptune emits more energy than it receives from the Sun, that its atmosphere is highly dynamic, and that its magnetic field is irregular and strong. The flyby also captured images of the Great Dark Spot and other atmospheric features, highlighting the turbulent and ever-changing nature of Neptune's weather. Since then, telescopes and space observatories have continued monitoring the planet, showing that it remains a world of constant motion, where storms, clouds, and winds evolve on timescales of days to months. Neptune also plays a crucial role in shaping the outer solar system. Its gravitational influence extends far beyond its immediate vicinity, affecting the orbits of objects in the Kuiper Belt and potentially contributing to the migration of icy bodies throughout the solar system. By studying Neptune and its interactions with surrounding populations, astronomers gain insight into the processes that have shaped the distribution of planets and smaller objects over billions of years. Neptune's presence may have been pivotal in scattering and capturing Kuiper Belt objects, influencing the architecture of the solar system and the delivery of icy material to inner regions. This dynamic interplay underscores Neptune's importance not just as an isolated world, but as an active participant in the solar system's ongoing evolution. Comparisons with Uranus, Neptune's ice giant sibling, further highlight the uniqueness of Neptune. While both planets share similar sizes, compositions, and distant orbits, their atmospheres and magnetic fields diverge significantly. Uranus appears relatively featureless, with a pale blue-green color and subdued weather patterns, while Neptune boasts vivid clouds, massive storms, and supersonic winds. Uranus's magnetic field is oddly tilted but less dynamic, and its atmosphere receives slightly less internal heat, potentially explaining the differences in atmospheric activity. These contrasts between the two ice giants provide natural laboratories for understanding how similar planetary bodies can evolve in divergent ways, influenced by internal heat, composition, and past events such as collisions or captures. Looking to the future, Neptune remains a compelling target for exploration. While Voyager 2 provided a brief glimpse, no dedicated orbiters have yet been sent to study Neptune in detail. Proposed missions aim to explore its atmosphere, magnetic field, rings, and moons more comprehensively, potentially revealing the composition of the interior and the mechanisms driving its extraordinary winds. Triton, in particular, is a prime candidate for further study due to its geological activity and potential subsurface ocean. Understanding Neptune in depth would also enhance our knowledge of exoplanetary ice giants, which appear to be common in other star systems. By studying Neptune, humanity gains a window into worlds far beyond the solar system, where extreme conditions challenge our understanding of planetary science. In the context of exoplanets, Neptune serves as a model for the many ice giants discovered around other stars. While observations with advanced telescopes reveal planets of similar size and composition orbiting distant suns, often in configurations very different from our own solar system. By studying Neptune, scientists can test theories of atmospheric circulation, internal heat distribution, and magnetic field generation under conditions difficult to replicate elsewhere. Its extreme winds, dynamic storms, and icy mantle provide a blueprint for interpreting data from these distant worlds, helping us understand how planets form, evolve, and interact with their environments across the galaxy. Despite its remoteness, Neptune continues to capture human imagination. Its striking blue color, relentless storms, and mysterious moons inspire visions of alien landscapes and powerful natural forces. The planet embodies extremes, powerful winds in a world of frigid darkness, dynamic weather in an environment dominated by ice, and a hidden interior that may conceal secrets about planetary formation in the early solar system. Neptune is not only a scientific treasure, but also a symbol of exploration, representing the boundless curiosity that drives humans to seek understanding even in the most distant corners of our cosmic neighborhood. Neptune's interactions with the Kuiper Belt reveal its subtle yet profound influence on the solar system's outer frontier. The Kuiper Belt, a vast collection of icy bodies beyond Neptune's orbit, is home to dwarf planets, comets, and countless smaller objects. Neptune's gravity helps sculpt this region, shepherding some objects into resonant orbits while scattering others into distant trajectories. For instance, Pluto, the most famous Kuiper Belt object, resides in a 3-to-2 orbital resonance with Neptune, meaning it completes 2 orbits around the Sun for every 3 of Neptune's. This gravitational dance prevents close encounters and maintains the stability of Pluto's orbit. Beyond Pluto, countless smaller bodies feel Neptune's influence, shaping the distribution and dynamics of the outer solar system over billions of years. Studying these interactions offers insight into how planets and small bodies co-evolve, and how gravitational forces can maintain long-term orbital stability even in a chaotic environment. The smaller moons of Neptune, often overshadowed by Triton, each tell a story of formation, capture, or collision. Proteus, one of the largest of these minor moons, is heavily cratered, indicating an ancient surface largely untouched by geological activity. Nereid has a highly eccentric orbit, swinging close and then far from Neptune in a dramatic elliptical path, possibly hinting at past gravitational disturbances. Other tiny satellites like Larissa, Galatea, and Despina orbit closer to Neptune, interacting with the faint rings and serving as shepherds that maintain ring structure. These moons reveal a system shaped by both violent events and delicate gravitational balances, demonstrating that even Neptune's minor companions play a role in the ongoing evolution of the planet's environment. The origin and formation of Neptune offer further layers of complexity. Models of solar system formation suggest that Neptune likely formed closer to the Sun than its current orbit, migrating outward over time due to interactions with Uranus, Jupiter, Saturn, and the surrounding protoplanetary disk. This outward migration may have had profound effects on the Kuiper Belt and scattered disk, shaping the orbits of countless icy bodies and influencing the dynamical history of the outer solar system. Neptune's migration is a crucial piece in the puzzle of planetary evolution, illustrating how planets are not static entities, but participants in a cosmic dance governed by gravity, collisions, and resonance. Understanding Neptune's formation also sheds light on why ice giants are so common in other planetary systems, often occupying orbits very different from the gas giants in our own solar system. Future exploration of Neptune is a tantalizing prospect for scientists and space enthusiasts alike. While Voyager 2 provided a fleeting glimpse, dedicated orbiters could reveal much more about the planet's atmosphere, interior, rings, and moons. Missions could deploy atmospheric probes to measure wind speeds, cloud compositions, and temperatures, offering a direct window into the mechanisms driving supersonic winds and storm formation. Triton, with its retrograde orbit, active geysers, and possible subsurface ocean, is a prime target for studying extraterrestrial geology and assessing potential habitability. A mission to Triton could involve orbiters, landers, or even penetrators designed to explore the moon's icy crust and detect any signs of internal activity. Such missions would not only enhance understanding of Neptune, but also provide analogs for exoplanet ice giants and their potential satellite systems, bridging our solar system studies with broader cosmic inquiries. Comparing Neptune to ice giants observed in other star systems reinforces its importance as a planetary archetype. Many exoplanets discovered in the past 2 decades fall into the Neptune-class size category, often with masses between 10 and 20 Earth masses and thick hydrogen-helium atmospheres mixed with water, methane, and ammonia. Observations of these distant worlds are limited, often revealing only mass, radius, and orbital characteristics. By studying Neptune up close, scientists gain a template for interpreting exoplanetary data, understanding atmospheric dynamics, internal heat distribution, and magnetic field generation under conditions far from their parent stars. In this sense, Neptune serves as both a laboratory and a benchmark, connecting the local solar system to the vast population of planetary systems in the galaxy. The extreme winds of Neptune continue to captivate researchers. Unlike Earth, where solar heating dominates atmospheric motion, Neptune's internal heat drives much of the weather, producing jet streams, vortices, and storms with unparalleled speed and intensity. Observations have recorded wind speeds exceeding 2,100 kilometers per hour, faster than any hurricane ever measured on Earth. These winds sculpt clouds and storms into striking patterns, some visible from Earth with powerful telescopes. Seasonal shifts, although occurring over decades, also modulate wind behavior, producing subtle but measurable changes in cloud density and storm intensity. Studying these winds provides insights into fluid dynamics under exotic conditions, helping to refine models of planetary atmospheres, from ice giants in our solar system to distant exoplanets far from their stars. Neptune's magnetic field and its auroras provide another window into the planet's energetic environment. The tilted and offset magnetic field interacts with charged particles from the solar wind, generating auroral displays near the poles. Though faint compared to Earth's northern and southern lights, Neptune's auroras reveal the dynamic nature of its magnetosphere and the ongoing exchange of energy between the planet and the surrounding space. These phenomena hint at complex interactions deep within the ice giant, where convection of electrically conductive fluids in the mantle generates the irregular magnetic field. Understanding Neptune's magnetosphere also informs our knowledge of space weather, radiation belts, and the potential hazards for future missions to the outer solar system. The rings of Neptune, though subtle, reveal fascinating dynamics. Unlike Saturn's bright, wide rings, Neptune's rings are dark, narrow, and composed mainly of dust particles with occasional larger rocks. Observations show that the rings contain arcs, dense clumps of material that persist over decades. The stability of these arcs is maintained by gravitational interactions with nearby moons, creating delicate balances that highlight the complex interplay between satellites and ring particles. These structures offer a unique laboratory for studying ring dynamics and the processes that shape planetary rings elsewhere in the galaxy. Even faint and distant, Neptune's rings exemplify the continuous evolution of planetary systems and the subtle forces that govern their structure. Neptune's distance from the Sun, about 30 times farther than Earth, subjects it to extreme conditions. Solar radiation is weak and temperatures drop to around -220 degrees Celsius, yet the planet emits more energy than it receives. This internal heat, likely left over from formation and maintained by slow gravitational contraction, drives the atmospheric turbulence and supersonic winds that define the planet's character. Understanding how such heat influences weather patterns in a low insulation environment has broader implications for planetary science, informing theories of atmospheric circulation, convection, and storm formation on other cold, distant worlds, both within and beyond our solar system. In addition to the physical and atmospheric properties, Neptune inspires a sense of cosmic perspective. Its remote location, mysterious storms, and icy moons remind us of the vast diversity of planetary environments. Studying Neptune is not merely an exercise in cataloging features, but a journey into understanding the mechanisms that govern planetary formation, evolution, and dynamics. Each storm, moon, and ring particle contributes to a story that spans billions of years, connecting the processes of the early solar system to the ongoing evolution of distant ice giants. Neptune embodies extremes: speed, cold, isolation, but also balance, resonance, and interconnection. standing as a testament to the complexity and beauty of our cosmic neighborhood. Looking toward the future, Neptune represents a compelling frontier for both robotic exploration and human curiosity. While Voyager 2 provided humanity's only close encounter, technological advances now make detailed missions feasible. Future orbiters could study the planet's atmosphere with unprecedented resolution, measuring wind speeds, cloud compositions, and storm dynamics. Atmospheric probes could descend into the dense methane clouds, revealing the processes that generate supersonic winds and massive storms. Landers or orbiters aimed at Triton could explore the geysers of nitrogen, smooth icy plains, and potentially subsurface oceans, offering a glimpse into geological activity in extreme conditions. Such missions would expand our understanding of ice giants, inform models of exoplanetary systems, and enhance knowledge of planetary formation in low-temperature, distant environments. The pursuit of Neptune is a testament to humanity's desire to explore the farthest reaches of the solar system, pushing the boundaries of engineering, science, and imagination. Neptune's study also informs the broader search for life beyond Earth. While the planet itself is inhospitable, its moons, particularly Triton, may harbor the conditions necessary for exotic forms of life. Subsurface oceans, internal heating, and cryovolcanism could create chemical environments where life might exist, similar to Europa or Enceladus in the inner reaches of the outer solar system. Exploring these moons not only addresses fundamental questions about habitability in extreme environments, but also connects our solar system to the growing catalog of exoplanets where icy moons might similarly harbor life. Neptune, in this sense, acts as both a scientific laboratory and a gateway for contemplating the possibilities of life in the universe. In the broader cosmic context, Neptune exemplifies the diversity and dynamism of planetary systems. Ice giants are common in the galaxy, yet our solar system's Neptune remains unique in its combination of atmospheric activity, internal heat, magnetic complexity, and satellite interactions. By studying Neptune, astronomers gain a template for interpreting distant ice giants around other stars, providing insights into the structure, formation, and evolution of planets under extreme conditions. Neptune demonstrates that even worlds far from their stars, bathed in faint sunlight and cloaked in ice, can host dynamic weather, active moons, and complex gravitational interactions. It reminds us that planetary science is not confined to Earth-like worlds, but encompasses a vast spectrum of environments, each contributing to our understanding of the universe. Ultimately, Neptune stands as a symbol of exploration, mystery, and the enduring power of curiosity. Its cobalt-blue appearance, relentless storms, extreme winds, and icy moons captivate the imagination and challenge our understanding of planetary physics. From its discovery through careful mathematical predictions to the fleeting yet transformative encounter by Voyager 2, Neptune continues to inspire scientists, engineers, and enthusiasts alike. The planet's hidden interior, complex magnetic field, and intricate interactions with moons and rings reflect the depth and sophistication of processes operating at the edge of our solar system. Every observation, whether from Earth, space telescopes, or future missions, adds to the story of a world defined by extremes, elegance, and ceaseless motion. As humanity looks outward, Neptune reminds us that the solar system is a dynamic and interconnected environment. The ice giant is not merely a distant orb in the night sky, but an active participant in the gravitational ballet that shapes the outer solar system, influences the Kuiper Belt, and provides a blueprint for understanding countless ice giants beyond our sun. Its winds, storms, and moons offer lessons in planetary dynamics, atmospheric physics, and the potential for habitability in unexpected places. Neptune's allure lies not only in what we have seen, but in what remains to be discovered, from the depths of its icy mantle to the potential oceans beneath Triton's frozen crust. The promise of exploration, combined with the mysteries yet unsolved, ensures that Neptune will continue to captivate and challenge humanity for generations to come. In essence, Neptune embodies the paradox of extremes, a world of icy calm cloaked in storms of unparalleled fury, distant yet intimately connected to the fabric of our solar system. It represents both a scientific challenge and a source of wonder, inviting us to expand our horizons and deepen our understanding of the cosmos. The windy ice giant reminds us that even in the coldest, most remote corners of space, nature exhibits power, complexity, and beauty beyond imagination. Neptune is not simply a planet, it is a testament to the resilience of curiosity, the triumph of discovery, and the unending quest to comprehend the universe we inhabit. As we continue to explore and study this distant giant, Neptune will remain a beacon of knowledge and inspiration, guiding humanity toward deeper insights about planets, stars, and the cosmos itself.